Hello, everyone. My name is Eduardo Sayalima. I'm a PhD student at the National Institute of Telecommunications in Natal and also a researcher at LabWalk. And today I will present the paper entitled Photonically-amplified Fronthaul toward 5G gigabit per second communications. And the authors are me and Professor Arismar Cerqueira Sodré Jr. Divided the presentation in four main steps: the motivation, then I present the photonically amplified Fronthaul experimental setup and the obtained results. Then I present the conclusion, future works, and main acknowledgements. So the 5D arose with three main scenarios called enhanced mobile broadband, aiming to increase the system capacity and the system throughput, reaching up to gigabit per second communications. The next scenario is ultra reliable and low latency communication to provide high reliability and latency lower than 1 millisecond. The third one is massive machine type communication, aiming to connect a huge number of devices provided by mainly by IoT. And to provide those applications, the 5G will have some enabler technologies such massive MIMO, network function virtualization, beamforming, software-defined network, network slicing, and millimeter waves. We will focus on millimeter wave transmission in the radio over fiber system. In addition, we will provide a different radio access network. In other words, we'll increase the conventional radio over fiber performance, and we'll focus on the BBU pool. So our technique is placed at the BBU pool and aiming to increase the electrical power at the remote radio unit. Now I will present the photonically amplified Fronthaul experimental setup, and we can see a experimental setup photography on the slide. Here we have a conventional radio over fiber in letter A, which is composed by a laser diode followed by a polarization controller, a Mach-Zehnder modulator, an optical amplifier, which can be used depending on the Fronthaul reach, 12.5 kilometers single mode fiber, a variable optical attenuator, optical power monitor, a photodetector, and electrical spectrum analyzer performs the signal evaluation. In letter B, we have the photonically amplified Fronthaul, which mainly differs from the conventional one, which they use a new laser diode, a new optical carrier, optical coupler, and the combined optical carriers are modulated by the RF signal, amplified, and launched at the highly nonlinear fiber input. In this way, the high optical power combined with the HLNF generate four-wave mixing products. We filtered the first, second, or third four-wave mixing product and launched it at the single-mode fiber Fronthaul. And the same occurred in this case, the signal are photo-detected and analyzed by an electron spectrum analyzer. When we compare the resultant electrical signals receiving the same optical power at the photodetector input, our system provide a higher electrical power, around 23 up to 27 dB, depending on the filtered four-wave mixing product. So here we have the four-wave mixing products measured at the highly nonlinear fiber output. We have inserted electrical signal with 1 gigahertz, and we cannot see the sidebands modulation due to our optical spectrum analyzer resolution. So here we can see the first, the second, and the third four-wave mixing products. So here, to increase the visualization, we have inserted a 28 gigahertz RF signal and compare the radio over fiber first and second four-wave mixing products spectra. So one can note the conventional radio over fiber in red, first four-wave mixing product in blue, and the second one in black. One can note the four-wave mixing products increase the sidebands in number and level. As a consequence, after the photo detection, the resultant electrical power is higher when compared to the conventional radio over fiber at the same optical power at the photodetector input. Here, in this case, we have compared the radio over fiber with the first, second, and third four-wave mixing products as a function of the optical power. And this comparison enables to find the difference between the photodetected electrical power. One can see the four-wave mixing products demand high optical power compared with the radio over fiber that presents a linear response. And it's worth mentioning the ending point of each curve, the optical power at the photodetector input is around 2 dBm. So comparing the ending point of the radio over fiber with the four-wave mixing products, we have a difference between 21 and 27 dB, which is defined as the electrical gain between the systems. And here we present the measured electrical spectrum around -15 dBm. One can see the spectrum is clean and no phase noise is noticeable. The last system evaluation was the digital performance. In this way, we have transmitted 1 gigahertz bandwidth 16 QAM signal at 28 gigahertz, which results in the 4 gigabits per second throughput. One can see the measured electrical spectrum, the eye diagram, and the constellation. The measured EVM was around 5%, since the 3GPP EVM limit is around 12.5%. The system provided 4 gigabits per second with plenty of margin, which can be used to increase the optical link or the system throughput, and after that, provide or enable the wireless link. As conclusions, we have efficiently implemented a photonically-amplified Fronthaul based on four-wave mixing nonlinear effect with the purpose of reducing or eliminating the need of purely electrical RF amplifiers. Experimental results demonstrate the photodetected electrical power increase as a function of the four-wave mixing product order, providing up to 27 dB electrical gain for the third four-wave mixing product. And the photonically-amplified Fronthaul provided 4 gigabits per second at 28 gigahertz in accordance with the 3GPP Release 15 recommendations. As a future works, we'll implement the proposed technique in a more realistic 5G RAN scenarios, composing by new RF signals in different frequencies. We'll perform the millimeter wave transmission after photo detection, enabling a high throughput 5G access point. And we also will try to use a high power optical amplifier and different highly nonlinear fibers for enhancing the four-wave mixing conversion and, as a consequence, the electrical power. Thanks, and that's it.